Well, thank you very much. So I'm Juan Carlos Flores. I'm representing Baker Hughes. We'll have a little introduction, but this is a real case. It's not a potential case. We actually print and produce, right? So it's actually a production example that we are going to share and actually present to you today. Baker Hughes, I'm Baker Hughes, and Tommaso is Octon. Go to the next slide, please.
It's here.
Oh, here. Okay, sorry.
I think.
There we go. Okay. So I'm part of the Baker Hughes team. I'm the director of additive manufacturing globally. And I look after the strategies on how we can actually utilize additive in the portfolio that we have, how we can help our customers. And I've been working with Baker Hughes for about 26 years. A lot of activity in the regulated environment. That's what we are actually focusing on in the energy sector. Tommaso is part of the Octon team, so the product manager for the monitoring, real-time monitoring on the portfolio that we are going to present today. Quickly, Baker Hughes, for those that do not know, is an energy company it's a technology company that plays in all the field of the energy sector. We have about 55,000 employees, 22,000 billions of revenue per year. And we have about 8,000 engineers that are actually in the portfolio. And we are present in 120 countries. Right? Octon?
Yeah, and we are working with Baker Hughes, and we are a software company. We have a very comprehensive portfolio of products that ranges from reverse engineering. We have a manufacturing operating system in the cloud to streamline production, and we also have software for build preparation, simulation, and monitoring and inspection, which is 3D Expert. So we are best in class for that type of products, very solidly working together with Baker Hughes.
Perfect. So now let's go to the problem that we're trying to solve, or what we were actually after. So we want to use additive manufacturing in our industrial processes, and we're trying to use additive manufacturing as a disruptor of the secondary metal fabrication processes, right? So we want to replace processes that have over 100 years, centuries, and during those 100 years, we have lesson learned, failures, we have catastrophic events. Then those lessons learned are put into regulations and product compliance and standards that we have to follow to not repeat those mistakes again. The liabilities in the energy sectors are huge, right? So we're talking about a failure is a catastrophe. It could be environmental, or it could be actually disaster on a city or on a community. So the liability for the operator or the manufacturer that actually put in practice those parts have huge impact. So we're not talking about simple parts. We're talking about critical components that we use in the industry for these cases. So the question is how we can actually cover the liabilities, how we can assure that that process is repeatable every time. And every time that we develop a new product, the sustainability of that product goes beyond just the first sample that we actually print, because we have to actually repeat that over and over because the liabilities are there, right? Okay, so with this in mind, we work on all the aspects of the energy. So we have, we're in the gas technology, the industrial. We're part of the industrial asset management for the industry as well. We touch the energy from the oil and gas, down drilling and extracting the oil, all the way up to producing electricity from the turbo machinery equipment. So we have the portfolio that is end-to-end in the energy sectors. When we started in the journey of additive 11 years ago right now, with a lot of investment in year on year, and we have probably about more than 1,500 parts that we have qualified in the energy sectors. I'm talking about parts that are not doorknobs or hinges or screw and nuts. We're talking about parts, as an example that we have below here, and we have produced over 100,000 parts of those that are in the field operating right now. So the question is how we repeat the process to sustain that reliability and that quality that we actually require that we owe to the customers. Now the next question is that those parts goes in the field, and it goes in the field and stays there for 30 years. I'm talking about a valve that goes into a subsea tree that has to sustain a 30-year reliability index. So we have vibration downhole, we have vibration in the water, we have corrosion in the subsea, and we have all kind of environmental risks if there is a leak, or if there's a corrosion, or if there's a crack, right? So we have to really guarantee a 30-year lifespan with no errors in that manufacturing process. And the liabilities of those mistakes are going to be really, really cascaded down. So we're talking about, if we put a valve today, we have to have the documentation and traceability for that part up to 30, 35 years by regulation and by law. So that's the main requirement for us. Now, go to the next one. For us, the key for us in the process control is, of course, the governance, the control, and the quality assurance. But we know for a fact that additive manufacturers have hundreds of variables through their process, and we have to actually monitor the hundreds of variables, and we have to identify which one are the sensitive variables for that process control to be stable. So in the last 11, 10 years, we have been working to determine which are the variables that we have to look, which are the ones that we can maybe don't look that much, and focus on the ones that are actually impacting the output of that production. So on that graph on the left, you say, okay, how we can do this practically, and we can do that economically. So we're a profit-for organization. So we do actually have to get profit. We don't rely on government subsidy, or we don't rely on equity funds, right? We have to actually make money. So we have to find solutions that goes practical and provide us an ROI versus the investment that we actually put for there. One of the first things that we actually noticed was, okay, guys, 60% of our quality notifications are coming from recording issues and are coming from simple, parameters in the machine that we could actually monitor. The rest could be actually quality notification that we can actually go deeper and we can actually analyze those. But if we can actually get 50% of our quality notification on the radar, we are really reducing our scrap 50% or our quality notifications. So these are just examples and how the process control are so critical. We have a recorder issue, we have a recorder line. The density of the material on those recording lines changes. We have a change in the one on the dimensions side. We had a case in which we just updated the release of the software, and the dimension actually changed the distortion of the part. And we're talking about tolerance that will hold that. This is a locking key in one of our casings that have to keep the tolerance pretty tight. Right? Now we have a case where we have an excess of soot particles because our flow was actually getting a little bit low because the filter was actually getting a little bit plugged. So we have excess of soot. So the density of those soots in the low side of the machine were bad, and we have a bad porosity or maybe a bad density. So you might get away with a print, and you think everything is good. 20 years from now, the part cracked, and then we have to actually demonstrate to our customer that the process was intact through the process of the printing. That's how we cover our liabilities, right? So the question was, okay, how we can monitor, prepare, and really have the documentation stable enough that we can actually be confident that we are okay with our liabilities, but at the same time, we can produce a report quickly to our customers. And if a regulatory entity comes and asks us, guys, can we actually provide enough documentation to prove them that the process was really sustainable? That's the question, how we do that. So some time ago, talking and evaluating, we started evaluating if we can actually dumb down that process monitoring in a way we can actually have a quick reaction, and we can actually have that documentation streamlined. So we partnered with Octon, and Octon helped us to actually develop that really quick, practical tool that we initiated, but they took it to the next level.
Yeah, thank you. So basically, we try to streamline the quality control over the whole production before to prevent anomalies, then during in situ monitoring in real time, cloud-based, in order to have basically the detection of this anomaly and being able to do something about it, but something for real that can prevent machine time loss and so on, and also material loss, of course. And then in the end, an inspection against also your parts together with simulation data, overlay of scan paths, in the end to create a sort of report that allows you very compactly to show that your part is reliable, that your parts that you have built maybe 20 years ago is not the problem. And so basically here we have a build and a simulation product, which is a GPU solver that allows to prevent issues like shrink lines, deformation, cracks in support structure and so on. Of course, you cannot predict everything. A physics-based simulator only predicts things that are predictable and not micro errors in the process or things like this, quality of powder and so on, things that you cannot really prevent. So what you can do then is you can connect with an edge device, we call it gateway, to a printer, any printer. We are printer agnostics, but in this case we work together with Baker Hughes and with SLM in order to provide this solution. And we have a best-in-class AI model that does also volumetric aggregation. You can export these results that run in real time and then bring them into 3D Expert, visualize them together with simulation, with scan paths, and start to think about root cause analysis if there was a problem. And if there was not a problem, you can go to your customers and tell them, here it is. This is the quality I provide for you. This is a little animation of actually this part that you can see there. I don't know, JC, if you want to mention something about this part.
Yeah, so this is the valve that goes in one of the, so that we have valve for this that runs in the refineries, in the nuclear plants, and in different chemical organizations they have to restrict flow, change the CV, noise attenuation. It's actually a production valve that we run on AM as a standard manufacturing process. So I actually took this valve, I went to the production floor and asked them last week, just cut one for me with a support structure so I can take it to Formnext. So it's exactly a production plant, the production part that we're running right now.
Right, and indeed, so this part is what we used as an initial test case to show. You can see here that the first stage we did like mechanical simulation and deformation, thermal analysis to prevent overheat, and this already you can start populating your report with this type of information if you had some pre-deformation that was above the... Can someone replay the video, please? So, well, anyway, the video was showing thermal analysis. And then after the thermal analysis, there is the real-time monitoring video that actually shows the online process monitoring, fully in real time, layer by layer, with 3D aggregation, and afterwards, 3D Expert again. How do we do it? How complex is that? How much you can actually use it in a production where indeed you actually have to make money? It has to be practical.
So the idea here was just as simple as taking the image from the machine as they are rectified, and hundreds of thousands of images that has been labeled with a production floor, and those has been trained to identify the most common problem that we had in that table that I showed you at the beginning, right? So the AI model is actually trained to identify quickly, okay, this is a potential issue, you have a recorder issue, this is a distortion that is coming up. So that's how the model actually works.
And we actually don't ask our customers to add any hardware to the printer. We purely work on vision. If you have a camera there, that's it. It has to be quick and it has to be useful. So we connected an SLM printer with our Octon gateway, and then from the Octon gateway in the operational workshop of Baker Hughes, then we stream data to a tenant of Baker Hughes on our cloud platform. And we basically show all these analysis in real time.
And that happened in real time. So
this is in real time.
It's not after post-processing. So as the images are coming,
right,
the edge device is actually processing those in the AI model, and it's automatically generated. Right?
So indeed, it's just real-time images of the accuracy that is good enough, not too high, not too low resolution, analyze the real time on the edge device such that we can have a very limited amount of data for speed that can go to the cloud in real time. And in the end, you can have an analysis, scroll through your images, scroll through your volumes, take actually an action during. If you have a problem and you see that an anomaly is growing, you can stop the print before. If it is affecting in a tray other parts because you have a recorder line, you can just skip that part, and that is a lot of time and a lot of material and money that you can save. The operator obviously have to take the decision for now because they're the expert. They have to evaluate if the anomaly is like say, severe enough in order to take an action. And then the next, after, let's say that the build goes well, it can still be that an anomaly that is not critical, the build still finishes, but it aggregates, it brings some little defects, some little anomalies, and is it good enough or not? So we can export the data, show it in 3D Expert, and create a traceability report for our colleagues in the workshop to basically check, okay, this is good enough, this is not good enough, very quickly, and if something is not good enough, they can delve deeper, go deeper, see the images, go and check inside of 3D Expert, what can we do with a different support structure.
So there are two values for us here. One, the first value is that real time we can actually have a flag if something is going wrong. So we can, the operator will get a message, a text message, or an email, hey, look in this machine, something is going on, he can go and check it out. That's the first thing. The second thing is that once the data is completed and the part is completed, all that imaging is actually indexed in the 3D CAD to the part that we actually produce it, and we produce a report that is a condensated report telling you how good was the print. Was it good enough to actually pass the qualification process, or we have to go on to an extra level to inspection, maybe a CT scan or a detailed level, so we can make sure that the part actually passes the screen. But the safe part is that if it's a critical component, we don't have to go a CT scan every single component. If the process have no flags, you just move on. If you have some flags, then those ones are the ones we identify for like more intense investigation or CT scan or any other volumetric that we can actually do.
So there will actually be an example on the screen. If you want, you can have one of these. And the reason why I say you can have one of these is that a lot of other processes have reports, but here we're not talking about 200 pages report. Actually, Baker told us very clearly, 5 pages max, that's your limit.
3, we get to 5.
I just added 2 just to be a bit safer. But 3 pages max, look at your parts, analyze them quickly, then go delve deeper if you really need.
Correct. So in a nutshell, right, we try to identify the formation, stressor, recorded interference. We try to look into the string length prediction, thermal, and overheat. With those simple identification from the image, very simple, with the AI model, we get those flags, and that helps us significantly in the production. Now, the next one, these are the pre-coded images. These are the pulse recorder, and this is the anomaly overlay. So we do those overlay and actually go into the 3D spectrum, and then we can get that report real time. The good thing about this is that the operator doesn't have to be in the machine all the time looking to the part, right? If something didn't flag as a red that it had to stop, and it may be a yellow that we put those thresholds, you can actually post-mortem go into the image and say, okay, look at and identify which layer was it. You have thousands of layers and thousands of images. The software will actually tell you, look into this one, and then you take your decision if you actually pass it or not. So it's very practical. Then, well, it's a base. I think we have the post-print inspection that I just talked about it.
Yeah.
And then this is the final report that Tommaso showed that we get for the production. Exactly. And then at the end of the day, so what we actually demonstrated, in this case, you go to the last one because we're running out of time, is that we achieve a cost-efficient way to monitor a process in a way that is practical, right? It's not really over the top. We have evaluated, pull monitoring, sound detects, but I think we landed up with something that's basic and easy to actually utilize. It's an open system. The idea for us in our strategy is to really go into an autonomous process, and this is just one step for us to go into that autonomous process, right? And that's really the case example that we have for you today. So, any questions?
If you have any questions.